So welcome to Math 408, L functions and sphere packing. So what I want to do today is talk about one of my favorite theorems in Fourier analysis, Poisson summation. So I've just made somebody a co-host so that you can monitor if anybody's trying to get in. I confirmed my biases before giving this lecture with an esteemed colleague of mine in the physics department here. And he agrees with me that of course every function is at least twice differentiable and decays rapidly. And I talked to him that there was a new research article coming out of one of the institutes in Japan where they may have found a function other than a Gaussian where you apply the Fourier transform to, but it hasn't been confirmed yet. When I was a student, this would have infuriated me, putting on assumptions like this. I wanted theorems proven in the greatest generality possible. Why are you putting in this addition? Because the proof is now nice, and we can get through the proof without being bogged down in tremendous technical issues. We talked about the decay of the Fourier coefficients. One way we got this was, well, if the function's in L2, we've got Bessel's identity, the sum of the absolute value f hat squared is bounded by the L2 norm, therefore the terms must be going to 0. The terms go to 0, all you need is the function to be in L1. This is the Riemann-Lebesgue lemma. That's a little bit more involved. And so what I want to do today is I want to prove Poisson summation for nice functions. I have been a practicing number theorist for about 2 decades now. I have never really had to deal with non-nice functions in these settings. And so you are absolutely encouraged to explore just how much can you remove these conditions, but for the practical purposes we're going to have, it's absolutely fine. Okay, so what I want to do is I want to start with Poisson summation. And so the goal is to show that the sum over n minus infinity to infinity of f of n is the sum and goes from minus infinity to infinity of f hat of n, where f hat of y is the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. So this is the Fourier transform of f. Whenever you see notation, you should always ask, is this good notation? When we do calculus, we have lowercase and uppercase. And the idea is you can quickly look and see, this is how the functions are related, antiderivative or derivative. The hat here is telling us it is related to the function f that we have started with. And so what I'm going to want to study is a new function, f of x, which will be the sum, and goes from minus infinity to infinity of little f of x plus n. What can you tell me about this function? What can you say? F of x is the sum of f of x plus n and goes from minus infinity to infinity.
Its behavior on the interval 0, 1 is the same as its behavior everywhere.
Boy, are you cautious. You've said its behavior on 0, 1 is its behavior elsewhere. Extremely cautious.
Periodic.
So this is where we're going to get into a little philosophical debate. If you say it is periodic, does it have to exist? Just because I wrote this down doesn't necessarily mean the function exists. You said its behavior on 0, 1 is the same as its behavior elsewhere. If it doesn't exist on 0, then I think you're actually in a better condition with that statement than this, because it is not clear that this function exists. One of my favorite jokes is a physicist, an engineer, and a mathematician are on a train going through the Scottish countryside, and they see a black sheep in the distance. And the engineer exclaims, I didn't know Scottish sheep are black. And the physicist goes, no, we can't conclude that. All we can conclude is that this Scottish sheep is black. And the mathematician goes, no. All we can conclude is there exists at least one sheep in Scotland which is black on at least one side. Be very careful in making claims and statements. Just because I write this down doesn't mean it exists. We hope exists and periodic. And so one of the examples is let's let f of x equal, and I came up with this example years ago, n to the sixth times 1 over n to the fourth minus the absolute value of n minus x if the absolute value of n minus x is less than or equal to 1 over n to the fourth and 0 otherwise. So when you look at this function, here's n. Here's a really small window, not drawn to scale, about n. And if you look at what's going on, when n minus x is 1 over n to the fourth, you get 0. When x equals n, you have 0 here, so it gets up all the way up to n squared. So the function has height n squared. It has thickness 2 over n to the fourth. The function isn't L1, it's integrable. The areas of each triangle is getting smaller and smaller and smaller as you go further and further down, but they're spiking up higher and higher and higher. If I chose this as my function, for most values of x, I'm not going to have any problem here, because eventually these are so close, I'm not going to be within that small little range of one of the integers. What's the one value of x that's problematic? 0. And so if we take x equals 0, it blows up. So this function is not well defined. And so this tells us that we're going to have to be a little bit careful when we want to do analysis like this. This is one of the biggest mistakes people make when they think they have an integrable function. They think, oh, if the function is integrable, then it must be going to 0 at infinity. No, it can be going large over small and smaller regions. If you wanted to, instead of having this 1 over n to the fourth, we could do it, I don't know, to some huge number. And then the function would be integrable, its square would be integrable, its cube would be integrable, but eventually it would not. And so you just have to be very careful about functions like this. So we're going to introduce a definition today for function to be nice. F prime and f double prime exist continuous, and there exists an eta greater than 0 such that for all x sufficiently large, the absolute value of f of x, f prime of x, and f double prime of x is less than or equal to 1 over absolute value of x to the 1 plus eta. To some extent, I can relax some of these conditions. If f prime is continuous, what do you know about f? I'm sorry? Yeah, it's got to be continuous, right? If the derivative exists, the original function has to exist. I'm not caring about the weakest possible conditions and what implies what. I'm not going to work with just the second derivative or something like that. Let's just assume my function, its first derivative and its second derivative are decaying at a certain rate at infinity. So that if you go sufficiently large, it's going to be less than 1 over x to the 1 plus eta. Why do you think I want 1 plus eta?
So we have to learn a new Greek letter.
No, if that was the case, I would have used this.
New?
You asked to learn a new Greek letter. Sorry. Yeah, I need to see the eyes crinkling because I can't see the mouth groaning. So why do you think I want 1 plus eta? Why not just call it eta? Why do I want it to be a little bit more than 1?
To make sure it converges.
Yeah, to make sure what converges.
The integral or sum of 1 over x.
Good. So this ensures integrals or sums converge. And that's why we want it to be at least 1 plus. Okay, and so some of the notes that I have is the first thing is a lemma that says this condition implies that the function f exists. So lemma, if f is nice, big F of x equals the sum, n goes from minus infinity to infinity, of f of x plus n exists. I'm not going to bother proving this for now. I'll leave this for you to prove. We're going to prove so many things that are similar that I'm going to see that this is usable. Yes?
Why do we need the things about the derivatives? Can't we just say if f of x like grows, decays faster than 1 over x plus the power of 1 plus eta, then the sum exists?
That would be enough, but in the argument that's going to come in later for Poisson summation, I'm going to need this to balance certain terms. And the problem is I could have a function that is nice, but there could be a spike in the first derivative. And so if we try to use the mean value theorem, the mean value theorem is one of my favorite theorems in all of mathematics. Anybody here a fan of the TV show Friends? Okay, we're beginning to change generations. Every episode, but I believe 2 is the one with. And so when I teach calculus and I do the proof of the fundamental theorem of calculus, I title the lecture, The One with the Mean Value Theorem. Because when in doubt, the mean value theorem is what we use to get whatever estimates we need. It's a poor mathematician's version of Taylor series. And for a lot of applications, that's all we need. It's just some rough estimate. And in the analysis that we're going to do, we need to show that certain sums converge. And one way to show that a sum converges, to show something is continuous, we're going to be looking at a difference of two things. And then you can often approximate their difference by their derivative at an intermediate point times the distance between them. So if my points are close to each other, and I have control over the derivative, then I'm in great shape. So I'm happy to prove this. We are going to prove other things that are similar to this. So for now, let's just put this in the bank. We'll come back to it later if there's demand. But it's going to follow very similarly to the arguments that we're going to do in a moment. And it seems it's reasonable that this should exist because, well, we've got decay here. And because we have the decay, the sums should converge. Okay, so we'll accept that lemma. So now what we want to do is, we know the function exists. What else do we know about f of x? It's been said before. Big F of x is periodic. What do you think is true about its derivative? The derivative exists, and what else? Periodic. What else? What do you think is true about the derivative of big F prime? Periodic.
And derivative is periodic.
Derivative is periodic. What else? Do you have any formulas for the derivative?
Negative f of x.
Negative f of x.
Positive. Oh no, negative big f of x.
We can differentiate term by term.
We can differentiate term by term. X plus n. Right? That the derivative of the sum is the sum of the derivatives. This needs to be proved. In standard calculus classes, you prove the derivative of a finite sum is the finite sum of the derivatives. So imagine we know that f plus g prime is f prime plus g prime. Then what we do is we play the parentheses game. If I give you f plus g plus h, and I ask for the derivative, this is the same as f plus g plus h prime. And this is the same as f plus g prime plus h prime, which is the same as f prime plus g prime plus h prime, and then you just drop the parentheses. And this proves that if you know the derivative of a sum of two functions is the sum of the two derivatives, it extends to 3. By induction, you can extend to any finite number, but you can't extend to an infinite sum. There is one infinite sum where it is very easy to prove differentiation term by term. Anybody know which series is just designed for this? No. E to the x is not
Taylor
bad.
series?
I'm sorry?
Taylor series?
Nope.
Geometric series?
Geometric series. So, and the reason is if I give you 1 plus x to the n plus x to the n plus 1, this is the same as 1 plus x to the n plus x to the n plus 1 over 1 minus x. The tail of a geometric series is a geometric series. So when you take the derivative, that gives you 1 plus x squared would become 2x plus 3x squared plus nx to the n minus 1. And then I get to do the quotient rule, joy. So I get n plus 1 x to the n, 1 minus x, plus, oh, I guess it becomes a minus when I take the derivative of this, minus x to the n plus 1. I think I've done it correctly. And then we can look and see, did I make a mistake? No. Okay. And then we can look and see what happens as n goes to infinity. As long as x is less than 1, even though this is growing, I've got an n here, I've got an x to the n. And so it's easy to see that this term is going to 0, and so this sum is going to expand out and become the derivative. This sum converges as long as x is less than 1. Question?
Don't we know that any function, as long as we're inside the radius of convergence...
So if you know that result, then yes. So if you know that you can differentiate within a radius of convergence, then you are fine. What I'm saying is you can almost prove that directly in the special case of the geometric series and not have to worry so much about dealing with the tail. It's unusual to be in a situation that's this lucky. Okay, so what we want to do is we want to prove that the derivative is the term-by-term derivatives. I just want to make sure I do things in the right order. Yes, okay. So that is the result I want to prove. So how should we calculate, how should we try to prove this? What should we start with?
Radius convergence.
Well, but we don't really have a Taylor series. We have a sum of a function at n.
But we're saying it converges to f of x for sufficient.
Yes.
Ages?
Well, we're saying it converges to, this converges for any choice of x. But how would you start calculating a derivative? What's your step?
Take partial sums or split the partial sums.
So to some extent, we would love to look at partial sums and see what happens from the end. And in fact, if you look at the partial sums, from some point onward, you can show that it's going to be a negligible contribution because it's a nice function. It's decaying at least as fast as 1 over x to the n plus epsilon. 1 plus theta.
Could you do something like going backwards with the integral?
You could do that, but
And then like use Fubini's theorem and switch them?
But how does every proof of a law from calculus, a differentiation law, how does every proof begin? You want to prove something about a derivative, what's step 1? Write the derivative. So let's look at f of x plus delta minus f of x over delta. And what do you want to subtract from that? we can subtract what we believe is the answer, the sum, and goes from minus infinity to infinity of f of x plus n prime. And what should that go to?
0.
That should go to 0. So now we want to look at f of x plus delta minus big F of x over delta. So that's going to be a sum, and it goes from minus infinity to infinity, of f of x plus delta plus n minus f of x plus n over delta minus f prime of x plus n. And I'll be careful here in terms of moving things inside sums. All right, so how would you approximate f of x plus delta plus n minus f of x plus n over delta? What could we use?
F prime of x plus n.
So you want to use f prime where? What theorem do you want to use? Mean value theorem, right? I debated having the Friends theme song cued and playing it right now. The mean value theorem is one of our most important tools for estimating something. I have, this is f of b minus f of a over b minus a. So this is going to equal the sum, and goes from minus infinity to infinity, of f prime of x plus, let's say, dn, minus the sum, and goes from minus infinity to infinity, of f prime, oh, sorry, it should be x plus n plus dn, sorry. Minus f prime of x plus n, where dn is in the interval 0, delta. Does this make sense?
Where did the DM part come
So we're using the mean value theorem. We go from x plus n to x plus n plus delta. So we have to evaluate at some point between x plus n and x plus n plus delta.
Oh, okay, I see.
So and then again, the idea is to show that things converge. We will eventually choose delta to be very small. And so when we look at this, we want to show that this is going to 0. We can take finitely many terms and deal with them, and then deal with the stuff going off to infinity. So if I truncate this sum, is it going to change things that much? Why or why not? Do these sums converge, first of all? I have two infinite sums here. I should be a little bit worried because I have infinite sums.
Yeah.
Why do they converge?
Because the derivatives decay fast.
Yeah, the derivatives decay fast enough that they converge. And so if I want, I can choose an n such that the contribution from all the pieces beyond n is less than epsilon, or less than epsilon over 3, right? So we can choose n so large that the contributions from the absolute value of n greater than n are at most epsilon over 3 for any epsilon. And if you think about how we're trying to show that this is true, we have to show for any epsilon greater than 0, there exists a delta such that this is going to be less than epsilon. So we only have to worry about n up to a certain point. So now we can look at the sum, say the absolute value of n less than or equal to n, of f prime x plus n plus dn minus f prime of x plus n. How should we approximate that?
Do you use like your eta approximation because you can bound it?
Mean value theorem.
I'm gonna use the second derivative.
When in doubt, use the mean value theorem. Right? This is just another example of the mean value theorem. This will just be f double prime x plus n plus, we now need yet another letter.
E.
I don't want to use E, don't want to use F.
Capital D.
Capital D. Why not? Capital Dn. And then what do we have to multiply this by?
Delta.
Not delta, close,
Well,
but
dn.
dn. And we know dn is between 0 and dn. So what do you know about the absolute value of dn? It is at most. So big dn is at most little dn in absolute value, and that's at most delta. So we're evaluating it at very close points. So this quantity here, by the triangle inequality, will be less equal to the sum n less equal to n in absolute value. We have a big delta outside, and we have f double prime of x plus n plus dn with absolute values. Could that sum be large? And remember, we can't approximate this with big F because big F could have some sign cancellations.
No one need it. Shouldn't be large, right?
I'm sorry?
I don't think it can be large.
No, because it's nice. So the second derivative also decays fast, right?
Yeah.
The second derivative also decays fast.
So
But that doesn't necessarily tell us how
you
good.
can bound it. Well, you can bound it by the sum.
We can bound it.
Yeah.
The bound could be large and the bound could depend on big N. But this has to be a finite sum. It has to be a finite value.
Bound doesn't depend on big N, right? Because you can just sum from negative infinity to infinity.
Yes, okay, so we could work that in and we should be okay with that. We have to be a little bit careful because this is not the same thing as the function big F because this point little dn is moving a little bit.
I think you can still bound it.
But we can still bound it because we know that eventually it's decaying
Yeah.
rapidly. And so we can make this, we can bound this. And we could actually extend it to all n. And then what we could do is for each of these intervals, we could actually look and see where's the function worst in those intervals. And because the second derivative is continuous, is going to have a maximum value. We know it's decreasing, so it can't be that bad. So this would be less equal to delta, the sum equals minus infinity to infinity, f double prime x plus n plus dn. And what you could do is you could just take the worst possible value between x plus n and x plus n plus 1. Take the largest value. And that sum will be finite because it has decay. And so this would be less equal to some constant times delta. So take delta to be less than epsilon over 3 times constant plus 1. I put in the plus 1 just to cover my ass. On the off chance that I'm looking at a function that's identically 0, that constant would be 0, and I would potentially have things blow up. So it's just safer to put in the plus 1 for protection. Not a big deal. And so this proves that the function big F is differentiable, and its derivative is exactly what you would expect. That if we have nice functions and we add them, we can differentiate term by term. So this is a truly wonderful result. Okay. And then a natural question to ask is, as I go through this, how can we weaken the assumptions and still have everything true? Okay. Any questions in what we've done so far? So I will leave the top line on this board that here is the definition of big F. It exists. It's periodic.
You can integrate term by term. Does that mean you must be able to differentiate term by term? Because it's solid.
I'm not sure. I would have to think about that in terms of what spaces you're on and what that might entail. If you're on a finite compact interval, that might be different than if you're on infinite one. So a function f of x is periodic with period 1. It's continuous, it's differentiable, it's continuously differentiable. Any theorems at our disposal now?
If it's differentiable, we can use the mean value theorem again.
We can use the mean value theorem.
Intermediate value theorem.
Intermediate value theorem. But we've been doing a lot of Fourier analysis over the past few classes. What theorem might be available now? We have a periodic function with period 1 that's differentiable. So we probably, as soon as you see a periodic function with period 1, you should be thinking Fourier series. Do we have any convergence result about a Fourier series for a periodic function with period 1 that's differentiable?
Don't we just have the Fourier series exists?
Well, we have more than just the Fourier series exists. I'm sorry?
Doesn't it just converge?
Yes, it converges to the value of the function. There's these annoying situations where you could have things exist, but do not converge to what you want them to converge to. We saw that for the function e to the negative 1 over x squared. Its Taylor series always exists, and it's 0 everywhere, which only agrees with the original function at the origin. This is not impressive, given that the Taylor series is f of 0 plus something that's 0 at x equals 0. You force agreement. So whose theorem is this?
Gaps.
No, but not a bad guess.
Euler.
No, also a good guess. You've probably done a good chunk of 17th and 1800s of mathematics. Dirichlet. So now we can use Dirichlet's theorem. Big f of x is equal to, say, s infinity f of x is the sum, and goes from minus infinity to infinity, f hat, well, let's do maybe m, f hat of m e to the 2 pi I mx.
What's the bold f?
I'm just really emphasizing what f we're looking at.
So
Because what's annoying here is we have two different f's, and we can be looking at a series expansion, a Fourier expansion on the interval 0, 1, or little f in the Fourier transform on all of minus infinity to infinity. So this is where you want to be very careful and specify where are you looking. So the natural question to ask is, well, what are these Fourier coefficients f hat of m? Do we have a nice formula for them? What function would you like to write f hat of m in terms of? Little f. And then note, big F of 0 is the sum and goes from minus infinity to infinity of f hat of m. That's half of Poisson summation. Oh, so no, yes. If those were related to little f. What else do we know about f of 0? It's just the sum and goes from minus infinity to infinity of f of m. And that's just from taking x equals 0 in the definition of big F. So if we can just show that this big F hat, the Fourier transform on 0, 1, the Fourier coefficient, is the same as the Fourier transform of little f, we're done. Because we already know these two are the same. So we know the sum of f of n equals the sum of big F hat of m. And all we want to do is replace a capital F with a little f. Okay? So let's compute f hat of m. That's the integral from 0 to 1 of big F of x e to the negative 2 pi I mx dx. Right. How would we try to calculate this Fourier coefficient? What should we do now? So how would biparts help us?
We could do like a udv.
Mm-hmm.
And we want, and that's the integral of b du. So if we let u equal f of x, we get little f of x.
So we could do that, but then that would start giving us things in terms of the derivative.
Right, big F as a sum.
So we write big F as a sum. So there were two things to try. One thing is to try to say, well, we've just proven some results about the derivative of big F. Let's get that into the game. Where we're using that is over here, so we can use Dirichlet's theorem. That's where we needed the differentiability. So this is the same as the integral from 0 to 1, the sum, and goes from minus infinity to infinity of f of x plus n e to the negative 2 pi I mx dx. Now what? Fubini, right? Can we use Fubini here?
Yes.
Why?
They're both finite.
So if we,
already shown that f of x plus n is going to be finite.
so 0, 1, it's a nice compact interval finite measure. If you put in absolute values, the absolute value of e to the negative 2 pi I mx is 1. Then we'll have this sum over here. And you should be able to show that that sum is going to be fine. Why is it going to be fine?
It's nice.
It's nice. And so what we can do is for each interval, we can look at what is the largest f could be between, say, 5 and 6, 6 and 7, 7 and 8. And we know that there has to be decay. So if we looked at some kind of soup function, so maybe g of n is equal to the soup of x in 0, 1 of f of x plus n. If we looked at something like that, because the function is continuous, it's going to have a maximum on each of these intervals. And because the function is decaying, we know that the sum of all these is going to be finite. So we can Fubini it. And again, we've learned that you have made it as a mathematician when your name becomes a verb. So we Fubini it, But we do not raise the blackboard because then it would kill that other stuff. And so we would get that this is equal to the sum, and goes from minus infinity to infinity. The integral from 0 to 1, f of x plus n, e to the negative 2 pi I mx dx. The last time it didn't go all the way up, so I was worried. What should we do now? When you see this integral, what integral do you want?
Want without the n.
So you don't want this n here. What could you do? We're trying to get, remember, the Fourier transform of little f. What do we need if we want to have the Fourier transform of little f?
F of x plus n.
Can't you sum like each interval which you integrate over, and then just integral over real n?
Yes. We integrate, first when n equals 0, we integrate from 0 to 1. When n equals 1, we're essentially integrating from 1 to 2. We have to be a little bit careful here because we have that n, right? Does that really matter? Why not?
It's just a constant.
Well, we want to say that this is the same as the integral from minus infinity to infinity of f of x e to the negative 2 pi I mx dx. But we have x plus n here and we only have x here. Is that legal to do this? Let's do it slowly. This is the same as the sum, n goes from minus infinity to infinity, integral from 0 to 1, f of x plus n, e to the negative 2 pi I m, x plus n minus n dx. Let's add 0. It's one of my favorite things to do. Do we care about this negative n here? That gives you an e to the negative 2 pi I m n. What does that equal? That equals 1. So we're very lucky because of what we have. This now we can piece it together as you wanted. We had to worry a little bit about the exponential. If instead of having an m here, if I had, say, a m thirds, I'd be in trouble. And now this is the integral from negative infinity to infinity, f of x e to the negative 2 pi I mx dx, which is just f hat of m. And that finishes the proof of Poisson summation. So I know the physics department has hats that are, in purple and have this on it for a hat. Nice hat here. Amazingly, the two things are the same. Big F hat at little m is the same as little f hat at m, but they are two very different hats. One hat is the Fourier coefficient of a periodic function on 0, 1. One hat, the other hat, is the Fourier transform of a function on minus infinity to infinity. So I am deliberately not giving you notes to look at before this. I want you to be thinking live as to how would you attack something like this. How would you piece all these things together? What things would you try to do? Why are we making the assumptions we do? Do we really need the second derivative? Yes, we actually saw we needed the second derivative when we were looking at the first derivative. Why do we need the first derivative? Well, we want to use Dirichlet's theorem. There are other arguments where sometimes we'll assume weaker things, and then have to use more measure theory or more powerful tools and techniques. Is everybody familiar with at least one situation where Fubini's theorem fails? Has everybody seen a situation where you can't interchange orders?
Yes.
Okay. Everyone has seen it? Yes?
I wouldn't be able to name
Okay. Here's a fast one. So in the interest of time, I'm not going to draw the entire upper quarter plane. I will draw only a finite subset. And we define the function. We're going to do a series AMN, AMN, and we're going to do them in different orders. And so here it's +1, -1, and then 0 forever. Here it's 0, +1, -1, 0 forever. 0, 0, +1, -1, 0 forever. If you look at each column, what does each column give you? 0. So if you do the columns first, and then sum over the columns, you get 0. But if you look at the rows, every row sums to 0, but the first, which sums to 1. So this is a situation where you can't switch the orders. And the problem is that the double sum of the absolute values is infinity. And that's why things break down. So in Fubini's theorem, you need the double sum of the absolute value to be finite. Have any of you taken measure theory? Okay, they might call it later the Fubini-Tonelli theorem when they try to extend it into more general product measures. But this is one of the big questions we need. I will be careful because this is being recorded. I will not give too many details. When I was a postdoc years ago, there was an interesting project I was working on where if we could get it to work, it would be a major result. And when you are a grad student or a postdoc, you want to have a couple of projects you're working on that will be huge pay dirt if they work. Should all of your projects be such? No, because if they don't work out, then you have no. So you want to have a balance. And if we could interchange either two integrals or an integral and a sum, then we win. But I was trying to justify it, and eventually I found that we needed a couple of conditions. We needed a quadratic function. It needed to be upward pointing. And we needed the leading coefficient to be negative. So if you can give me a parabola that points up with leading coefficient, the coefficient of x squared being negative, I could then justify the interchange. Yeah, that paper has still not been written. There is no such function. So when I talk about, step one is prove something exists, you really need to do this. And you could argue that maybe we should have checked a little bit earlier and not spend as much time as we did, thinking, oh yeah, of course we can justify. Most of the time you can justify the interchanges. But we were having trouble, and I was trying to figure out precisely what is going wrong, what is the difficulty. And eventually I realized, oh, there's no way this is going to work. There's a fundamental obstruction to this method. That doesn't mean the result is false. It's important to note the difference. It just means you will not reach that result through this path. All right, so this finishes up a good amount of Fourier analysis. Depending on my mood, I might do one or two more results in Fourier analysis just because it's such a lovely subject, but we've now at least reached the point where I can now go back to my notes from my colleague where we needed Poisson summation for certain analysis. And so again, Poisson summation is a powerful tool. And there's going to be at least one homework problem where I ask you to just use Poisson summation to evaluate certain sums. And this is where Dirichlet's theorem, I think it's still on the board, is so valuable. is if the function is periodic and differentiable and the derivative is continuous and nice, you can replace your function with your Fourier series. And if you just take x equals 0, now you have a sum of the Fourier coefficients. So if you can recognize the sum that you want to evaluate as the coefficients of the Fourier series of a nice function, you can now evaluate those sums by saying, that's just my function evaluated at 0. The difficulty is if I give you a series of Fourier coefficients, can you recognize the function it comes from? What you often do is you start off with a function that you can work with, and you calculate its Fourier coefficients and say, now I know this sum. But you could try to go in the other direction as well. All right, so this is a good place to stop.